Hi, I'm Philip, and in this video I will show you how to compare a scanned file to the original step file. So for my use case here, I have this 3D printed mold. This is a mold for like a body kit for a Porsche. This will be like a door panel, a new one. And this is the one section. Here in the background you can see 3 more sections. And since this is quite a large PETG print, and initially I mainly used PLA Plus for printing large body parts for the project, but for like the direct molds, the fractional heat temperature, the point when it softens is simply too low with PLA Plus. So I had to step up to PETG, and now I want to make sure that the parts are still in spec and there's not too much deviation between my step file and the final printed part. The accuracy of the scanner actually will not matter in comparison to the printing tolerances. So I just did a accuracy test with the Einscan Rigil I used for scanning, and in laser mode it came out to roughly a hundredth of a millimeter. So the printing tolerances, especially like with a 0.8 millimeter nozzles, will be way worse. For scanning, you can see I just placed my my part on the table, on the workbench, placed marker cards around it. So these are basically like aluminium business cards with markers I glued on, and some marker geometries, and some very few marker points on the part itself. These are simply necessary because you have like this very big, large, flat area with like some overhangs here to the side, and then the markers only on the table won't be enough. And what you have to keep in mind, the closer the part to the marker, the more accurate they are. So if I only would have placed like a marker here in the bottom and scanned right here up the top, the accuracy and actually the surface quality will be a bit impeded. I did the processing of the scan itself all on the scanner in standalone mode. So I scanned in standalone mode at 0.5 millimeters and also processed it. I did 4 scans of the 4 mold pieces. Each scan took roughly, I think it was like 2 minutes or 2 or 3 minutes. The post-processing time is basically 20 seconds or 30 seconds for the point cloud optimization, and then 2 minutes for the meshing, and just this while cleaning up my equipment and putting away my equipment. For the comparison, I will be using Quicksurface, and this is the Pro version of Quicksurface. I'm not completely sure if all what I'm showing you will also be possible in the light version. Actually, there is now, with the latest Quicksurface release, a new button to switch between the light and Pro version. Of course, for Pro features, you need a Pro license, but this would theoretically give you the option to try out both modes, maybe if you have like the 30-day testing license. First step will be importing my reference geometry. It's here under in the start menu, import CAD. For this, I just choose my step file I exported from Fusion and open it. And what's quite nice with at some point, they adapted the import behavior, so it automatically splits up my my unique bodies in the step file. I can still combine them. So if I now select all of them, go under CAD and combine, it creates me my uniform part. But now let's reverse this, because I will be comparing the similar pieces, and for alignment this is easier. Next step is importing the scan data. And for this, I just here in the downloads, I have my my 4 STL files. So the first one, and with Control I, import scan data. Then I mixed up the shortcuts. The second, now the third one, you can also select multiple scan files or STL files at the same time, but they need to be in the same folder. So if I buttered and moved all of the 4 files in the same folder, it would be quite easy now, but it is what it is. And as you can see, the alignment is now completely off. And I also have like a lot of table with the scans. So the first step will now be cleaning up the scans a bit. And for this, I will just hide the solids and focus on the first scan, and theoretically I could do the prepare scan option, and the prepare scan option will take me through like all the submenus. First the reduction of the polygon count, so here from 2 million to 1 million points, then the like mesh editing, the alignment tab, the symmetry tab. But because I will align it either way to the step files, and I'm not having any symmetry in my parts, I will just use the edit scan. So I select it, edit scan, and then yeah, I will just clip out what I'm needing. This, like, I can use this. Like, this is the brush I use most often. This is like the freehand selection. So but it also creates like this straight line in the bottom. So I can just line it up like this and select all the parts I'm needing. Now I can reverse the selection and delete all the unnecessary points. And this looks fine, so I can close it. And as you can see, the polygon count is already greatly reduced because all the unnecessary data is gone. And I will just, continue with all save. So now the next one, and as you can see, I accidentally mixed it up here a bit. And by pressing Control and Alt, you can invert the selection, or invert the paintbrush, better say. So let's delete the data here. Then we will move on to the third part. This is maybe a bit of a boring watch, but you can skip it if you're not interested. So, and the last one, they even captured it captures some of the backdrop of my workbench. So the scan range is quite large. You can of course always like limit the scan distance the scanner picks up data. And now what you're seeing doing here, basically I'm seeing I have 3 individual meshes, but I only want the center one. So I can just edit, click on the one I want to keep and say this is the only one in my scan. So this is like the quick option. So now this looks good and we can start aligning. So let's start with the first piece. This is like the front end of my mold. So let's match this up. This is this one. And I can now use the point picking for aligning. So say basically picking endpoints, and I can just do it like this. And maybe a 4th point. So 4 points are generally speaking like good enough. And what you're seeing now, it is roughly fitted. And what I'm doing now is fine alignment. So this is the rough fitment, and I can now fine align. We will start with a search tolerance of 3 millimeters and now go up step by step. So I will now switch to 1 millimeter fine alignment, and maybe let's do it again with 0.5 millimeters. So it will try to match them up as close as possible. So this looks good, and I can now do the alignment with the next 3 parts. I just finished recording the alignment section of the video, and I noticed that I chose the wrong approach for alignment, because a problem with the 3D print is that the PETG is liking to shrink after printing. So if we look here, we have like on this side there is very good alignment, or if I now make a comparison of the parts, it looks good, and on the other side we have like the shrinking problem. And it's same for like these parts. On the one side it fits, on the other side it's not fitting at all. So roughly nearly 1 millimeter of shrinking. 3/3 of a millimeter of shrinking. And therefore the shrinking outskirts of the 3D printed part, they cause the alignment to be off, because they are also included in the alignment algorithm. And the main part I'm interested about is the center section of the pieces. So where the actual mold will be kept, or will be used for. And therefore my alignment must also be for the center parts, because these are the parts that are relevant to me. So now I will actually move the parts out of the way, or the scans out of the way. And for this, I'm using just the interactive alignment, it is called. So, and then I can edit my scan data to only include the relevant part, or to hide all unrelevant parts, and then I can align again. For this, I will show you like a demonstration with one piece and then speed through the others. But let's start with this one. And this is the workflow I should have used from the beginning for all pieces. And basically, my goal is now I will edit it and I will hide all of the outer parts of this print. So only these center pieces are used for alignment and fitting of the alignment. I can reach this by simply now using the brush tool and then hiding the outer parts, just like this. Like this, and I can now hide it with the eye. And the hiding doesn't completely delete the data, it just hides it, and the good thing is, as long as the data is hidden, it is also not used for example, alignment. So I can now go again into the alignment tab, use the endpoint alignment, starting with like a rough alignment, and then getting like, sharper again, or more detailed with every iteration. Like this, and then maybe one here. So this is the first preview, and now I can use fine alignment. We'll start with 3 mm fine alignment, and then you can go down to 1 and maybe 0.5. But at some point with the fine alignment, it still will stay very static. So now there isn't happening much more. And if I now have a look at the analysis, it looks very good. So let's only pick a few points. And it looks better. I will show a comparison later when I did all the other parts, but now I can select the part again, double click it, and show all my print parts again. And what's now quite interesting, if I now look at the comparison, you can see the shrinking very drastically. So I'm basically having like 0.3 to 0.4 millimeters of shrinking on all sides. So this is actually way more than I thought. And on my PLA Plus prints, I haven't seen this much of shrinking problem at all. But we will still try it with this mold type. Now let's speed through the other parts. So now I finished aligning all of the prints, all of the scans of the prints, and now I still have to like unhide all the missing parts. And now this looks much better. So if you now have a look at the analysis, and especially here the top parts. So previously with the first methodology, they were like 0.7, 0.8 millimeters off. But now let's maybe top this to 0.2 millimeters of tolerance, and this is, I'm quite happy with the outcome now, and this looks a bit more like in spec. Of course, here on the shallow overhangs, we have the stair stepping of the 0.4 millimeter layer lines or layer heights, but this looks now way better. But for tolerances, I will mainly look at 0.1 millimeters. So this gives me a bit of a better feeling. So here we have like some section of the print where we have a bit of a wavy pattern in the surface. So I should have used a bit more like contacting support to the side. So basically I use supports on the print that are going to the side of the print to make it a bit more stable in the high up areas. And for this to work, you have to look at the slicer setting. It's called XY pattern or XY spacing between support and bridge. So this is normally used to ensure that there is enough space between the support and the part itself, so it can be easily pulled off, but I want the contrary action. I want it to stick to the part, so it's actually like a bracing. But yeah, this looks quite nice, and now maybe let's open the my initial pictures of the comparison I did. So this may give us a bit of a better feeling. So this was the initial test, or the initial alignment I did with like the, where I used the whole part for alignment. So I didn't hide the outer parts and directly used the whole parts, or directly aligned them. And as you can see, especially like here in these top areas, there we have like a completely different picture now. And also like the general overview looks better. But yeah, so keep in mind for alignment, especially with 3D prints, the parts are shrinking, and then suddenly all your geometry is a bit off. This will also show in the alignment results. Therefore, I hope you enjoyed. I hope you could learn maybe a few things for the next time you have to do similar tasks. And goodbye, and until the next video.